Hello students, today we will read about the continuous charge distribution. Like till this class and before this class we were dealing with the discrete charged units. Now it's time for us to step ahead and understand if there is a continuous trail of charges. If there is a continuous trail of charges, these charges are not distinguished as Q1, Q2, Q3 but as a system. Q system. How should we deal with such a problem? Okay, it is impractical to work in terms of discrete charges. We need to work with continuous charge distribution. One of the example is on a surface of charged conductor, it's impractical to specify the charge distribution in terms of location of the microscopic charge constituent. If we are taking one spherical surface, we cannot define, like for a given area we are having 10 charges, but for the whole surface we can define that on the surface the amount of charge is present is equals to Q. So at such level where the microscopic levels are included, we cannot go with the single charges. We have to work with the continuous distribution of charge. It is more feasible to consider an area element del S on the surface of conductor big enough to include very large number of electrons and specify the charge del Q on that element. We then define a surface charge density, that is sigma, at that area element, and sigma is given by the charge distribution over the given surface area. Now we have taken this sphere. From this sphere we have taken a big space having charge distribution up to del Q, and the area of this sphere is del S. So the distribution surface charge density distribution is given with a symbol sigma, and it is given by number of charges present per unit area or in the given area. Number of charges present in the given area. Surface, it is surface implies the surface of the material, charge implies the charge, and the density. What does the density implies? Density implies how many numbers with respect to the given amount, volume, length it is there. So when we are going with the surface charge density, we consider area. With respect to area, we tend to find the number of charges. This can be done at different points on the conductor and thus arrive at a continuous function that is called sigma surface charge density. Now surface charge density sigma ignores the quantization of charges and discontinuity in charge distribution at microscopic level. Sigma represents the macroscopic. They are removing discontinuity at microscopic, but sigma is a quantity which explains us macroscopic phenomena. Macro yani it means bada, the bigger space. Surface charge density smooth out average of the microscopic charge density over an area element del S, which is large microscopically but small macroscopically. Units for the sigma are coulomb per meter square, because it is charge per unit area, so it is coulomb per meter square. See, this is the area we have considered, and from this area we are trying to find the surface charge. The linear charge density. Linear implies something related to line charge density on a particular line. It is a two-dimensional concept that is denoted by lambda of a wire is defined as lambda equals to charge upon the length, small charge present over the length L, del L. Del L is the small line element and del Q is the charge contained in that line element. Units for the lambda are coulomb per meter. That is charge upon length. Now volume charge density that is simply termed as charge density also. It is the charge density which we are using most of the time, is denoted by rho, and it is given as del Q over a volume of del V. Del Q is the charge contained by macroscopically small volume del V. Like microscopically it is big, but what about macroscopically? It is small, and SI unit for it is coulomb per meter cube. Similar to the continuous distribution of mass in mechanics, continuous distribution of density of fluid in the fluid dynamics ignores its discrete molecular constituents. Even when we go with fluids, fluids also have small corpuscles, but they all together come with the effect of viscous force and tend to form a single droplet or a single stream of the fluid. Field due to the continuous charge distribution is obtained in same way as discrete charges. Like if we want to calculate field for the continuous charge distribution, it will follow the same formulas and same laws, like Coulomb's law for defining force and superposition principle for multiple charges. Suppose continuous charge distribution in space has a charge density of rho. Let the position vector of any point in the charge distribution be r. The charge density vary from point to point and a function of the r, as we have seen, like field lines are lesser over here, more over here. So according to that, these position vectors are changed. It will change the charge density also. Density over a given volume will also change. Divide the charge distribution into the small volume of element size del V. Charge in a volume element is given as rho del V. See, we have rho equals to del Q upon del V. So what about the amount of charge present in it? It is equals to rho into del V. Okay, this is what we have taken. Considering any general point P inside or outside the distribution with position vector capital R, electric charge due to the charge rho del V is given by Coulomb's law. That is, electric field is given like this: del E 1 by 4 epsilon naught into charge density into volume, that gives charge. This gives us the amount of charge by r square. R square is the position vector. So r dash is the distance between charge element and point P, whereas r cap is the unit vector. Now by superposition principle, the total electric field due to the charge distribution obtained by the summing over electric fields due to the different volumes, a volume element, is given as this: E equals to 1 by 4 pi epsilon naught sigma over all the small volumes. All these small volumes gives rho del V by r square into r cap. Rho, r dash and r cap all vary from point to point. We should let the volume be 0 and the sum then becomes an integral. Using Coulomb's law and superposition principle, electric field can be determined for any charge distribution, let it be a discrete charge distribution or a continuous charge distribution, or part discrete or part continuous. So for any sort of charge distribution, Coulomb's law and superposition principles are valid. So now we will summarize everything in a single page to understand what we have understood by the charge distributions. So for today we have read continuous charge distribution. continuous charge distribution. Okay, in this what we have seen, there are two concepts of microscopic level and macroscopic level. At microscopic level, these charges seems to be discrete unit. Here we can define a single electron, a single proton, single charge and everything single-handedly, okay, single. But when we aim at macroscopic level, these charges seems to be a continuous trail. Charges seems to be continuous. Now we will aim at a line at a particular surface and for a given volume. Now in this we have taken a small length. In this we have taken a small area, and in this we have taken a small volume. This length, area and volume are small with respect to macroscopic world, but are big enough with respect to microscopic level. Okay, so when we have taken this small value, we will denote it as del L, del S and del V. We need to find the charge distribution for this small length, small area and small volume. We need to find what? We need to find charge distribution. Okay, so for the smaller length, the charge distribution will be given by lambda, that is linear charge density. For the smaller area, it will be given by the surface charge density, and for the volume it will be given by the charge density, simply the charge density. Okay, this linear charge density is denoted by lambda, surface charge density is denoted by sigma, and charge density is denoted by by rho. So this lambda will be given as charge over the length, charge present over the length del L, sigma will be given charge present over the area del S, and rho will give charge present over the given volume. Now the SI unit for this is coulomb per meter. For this it is coulomb per meter square, and for this it is coulomb meter cube. Now hope this thing is clear. The other thing which we aim at for any sort of charge distribution, Coulomb's law and superposition principle are valid, as we have seen in the previous slide. So that's the summarized form of today's class, and that's all for the today's class. We'll meet in the next class with one more interesting topic. So see you. Bye bye.